DC-Dewatering is handling dewatering constructions or the calculation of groundwater lowering. If we create a new file, you see at the left, like in most of the programs, the most important functions. And first, I would like to show some configuration parameters which are important for the analysis. And we can select settings, configuration, to predefine these parameters. So by default, if we have a foundation pit with a certain depth, we want to have the groundwater at 0.5 meter below the depth of the foundation pit. We have different additions to calculate as a safety for the pumping capacities. And what is important for the units, you may calculate in liter per second or cubic meter per hour, which is a factor of 3.6 between these two units. For the reach or range of a dewatering construction, there is an older formula by Sichart, 3000 multiplied by the lowering S and square root of the permeability. And there is a newer type published by Weihrauch, which is so-called minimum range. And we have as well an approach by Weber, which is not used very much. So if we have these configuration parameters, we can start with the basic parameters for the analysis. First of all, we have to know where is our groundwater level without dewatering. So the depth is, for example, 1 meter and 50. And in which depth do we have the aquitar, which is the base, the impermeable base soil layer. It might be at a depth of 18 meters, for example. The storage coefficient is used only for a time-dependent reach. We will see this later. And for the analysis fundamentals, by default, we calculate with the maximum possible pumping capacities of all the wells. So Q is the sum of the capacity of any single well. And as well, we can apply only the required pumping capacity, which means if we have too many wells, we don't want to have too large water depth. So we reduce the capacity and use only the totally required capacity of the wells. As an option, we may also predefine the capacity. If you want to calculate an existing situation, you can define the rate at which all the pumps are acting in your construction. There may be some inflow from rain, which is only used in special analysis types. We will see this later. And the groundwater situation may be unconfined, free groundwater flow, or confined groundwater, which has an impermeable layer on top, or a semi-confined groundwater. There might be a water level which is determined by a river or by the sea in a certain distance. And for quite impermeable soils, we can use vacuum well points with a special analysis approach. What is important for vacuum well points, if we look in the manual of the program, for this type of analysis, we only have two formulae. One for the required total pumping capacity, which is increased, and the capacity of any well, which is increased as well. And this increase will only help us if the factor for the well capacity is higher than the factor for the required capacity. And this means that the factor U, which is the unevenness coefficient of the soil, U or Cu, should be quite low, values between 2 and 5, for example. If U is very high, for example 20, this will not help us at all, because the increase for the single wells is in this case smaller than the increase for the required pumping capacity. So this only helps us if the U or Cu value is quite low. Now we want to calculate an unconfined aquifer. And the most important thing that we have to know is the permeability of our soil. We can define several soil layers here. We have the best results if there is only one constant soil layer, because the total pumping capacity which is required has to be calculated soil layer by layer over the depth. And for the water level at a certain position, the water level Y has to be calculated with a medium coefficient between all the soil layers. So if there are different soil layers available, this gives some difference which is not optimal for the results. So we use only one soil layer, gravel, for example, which is available down to the depth of the aquifer. And for the permeability coefficient, Kf, we can switch with these arrows over factors of 10. For example, if we want to have 5 and 10 to the power of -4, we can switch with these small arrows. We can define the porous component, so which part of the soil is filled by water, for example 30%, to calculate the sum of the total volume of water inside of the foundation pit. And only for impermeable layers we need the unit weight and the unevenness coefficient, which is only used for vacuum wells. So we have this one soil layer and can then define our foundation pit, which can be an arbitrary polygon. In this case, we just use a rectangle as a first example, 20 and 10 meters. And we need the depth of this foundation pit, for example, 5 meters. There are two special analysis methods that we will look at a little later. So at this time, we only need the depth of this foundation pit area. Now, the second thing that we need is the type of well or the size of the wells. There might be as well a circular subsoil pit. And now we want to define a well at this corner, for example. We have a position of the well, the diameter of the bored hole which is used for pumping, and the bottom edge of the well is, for example, 18 meters. If the well does not go down to the aquifer, if it is shorter, we don't have only a horizontal inflow, but additional inflow from below. And in this case, we have so-called unperfect wells, where we have to add a certain factor for the required pumping capacity. In this case, we go down to the aquifer. So we have our first well. Now we can make a first calculation over this analysis dialog. And it is important that this is first only a rough estimation, because we calculate the capacity of this well, which has quite a large range or reach. But if we have several wells, which might be very close to each other, then one well will take water from the other, so they influence each other. And as more wells as we have, the more will the capacity of the single well be reduced. So the program first tells us we need 2 wells to reach this total capacity. But if we add a second well and calculate again, we see that we will need 3 wells. So these 2 wells, which are not very far from each other, influence each other, and we don't have the total capacity that we had before. It's now 25 liters per second instead of 28. Now, instead of creating the wells one by one, we can also use an optimization function, which is shown here in this icon. If we want to optimize the wells automatically, we clear the available ones and can now define which lowering do we want to have. We have a water level of 1.50 meters. We have a foundation pit at 5 meters, so we want to go to 5 meters and 50, which defines a lowering of 4 meters. Then we have the diameter of the well, the depth of the bottom edge 18 meters, and they should be placed with a distance of 1 meter to the foundation pit. If we enter a negative value, this would mean to place the wells inside of the foundation pit. So -1 would be 1 meter to the inside. We can have the position of the wells optimized as well. And with the computers today, it's not so time consuming that it was years ago. So if we start the calculation, this is going very fast. And you see with 3 wells, our dewatering is fine. We have a total capacity of 68 liters per second, which is required. We have, for the first well, for example, we have the capacity of 22 liters per second. The second one is 23, third one 22, nearly 23. So in total, these 3 wells are sufficient to reach this dewatering that we need for this foundation pit. We can as well define section lines. For example, one through the foundation pit. This can be a polyline, and we stop the input for this line with the right mouse button. So we have section 1 here, and another section line through the wells. This should be section number 2. Now we can switch to the graphics to see the results. We can again change the lowering, which is required. And we can display the water depths with lines or with color areas. And now here you see that at the wells we have deeper water levels, and inside of the foundation pit it's less deep. And we have the critical point at this position here. And now we can control that with a cursor. We have this icon here for the lowering. And we see that here we have more than 7 meters depth of the water level near the wells. And at the critical point, we have exactly the 5.50 meters that we wanted to have, which is the base plus a safety of 0.5 meter. So this is sufficient for the dewatering of this foundation pit. And if we continue with the page down button, we can see the section lines. We can change to a larger scale here for the sections 1 to 120, for example. So we see that at every point the water level is below the 5.50 meter level. And where we go through the wells, we can see the water level in the wells and the range between. So again, we have more than 5.50 meter. So this dewatering is fine for our foundation pit. We have detailed results as well. If we go to the results here, first we have the input parameters, the groundwater depth, aquitar, the soil layers, and the subsoil pit. And on the next slide, we have the results for the wells. So for any well, we have the water level in the well, water level below surface, the wetted filter height, and the capacity of any well. Then there are certain additions to calculate, and for a theoretical pumping quantity of 49 liters per second, with all the additions required, we have Q max of 68. And for this capacity, we need 3 wells. We have 3 wells available, so this is sufficient. And we see the maximum capacity for all the wells, which determines the pump to be used and the required filtering. The range or reach of this dewatering is about 470 meters. And then we see the water levels at any point of the foundation pit, at the center and at the critical point. So for any position, we have at least 5.50 meters, which is half a meter below the base. And if we switch down the page down, we go to the graphics again. So one thing is important. We have the possibility to enter any polygon of foundation pits. And there might be different sections with different depths. So as an example, if we have an additional part of foundation pit here at this position, and this should be for a depth of only 3 meters. Now we have a larger area, and if we calculate again, we see that is still sufficient. Okay, I wanted to show you an example where it's not sufficient. We can use a larger area here. So just dragging the points. And in this case, as we have a larger area, our available capacity is not sufficient compared to the required capacity. But this is calculated for a lowering by 4 meters, because at this point here, we want to go to 5.50 meters. We won't need this depth for the second area here, because with a depth of 3 meters, it would be sufficient to go to 3.50 meters. So for concerning this different depths, we can use here the option adapted to depth. This means that the dewatering is only calculated to a depth which is required at any different point of any section or a part of the foundation pit. And you see, if we calculate adapted to depth, then the capacity is sufficient because our total required capacity is less than it was for a complete lowering by 4 meters. And if you look at this result, I can draw the section line. I have to look for the endpoint. The section line through both of these parts and go to the graphics again. We calculate now adapted to depth, which can be changed with double click. Here we have adapted. And for the color areas, we can as well enter different steps to have even numbers, for example, a spacing of 10 centimeters, which gives us 31 colors for this area of results. And now we have the critical point again here, because this is the deeper section, deeper part of the foundation pit. And what we see in the sections here, that we have a less lowering here. We don't go to the 5 meters and 50 that we had before. So the 3 wells at this deeper foundation pit are sufficient for the less deeper one. So we don't need extra wells for this second part of the foundation pit. So at any point, we have a sufficient depth compared with the depth of the foundation pit. So far for the basic analysis, which is a free groundwater flow. Now if we go back to the first foundation pit, we can select the second one and delete it with the delete button or with the cut icon. We have one foundation pit, and when double clicking this area, we can select one of the special analysis methods. One option is a waterproof enclosure. So there might be a sheet pile wall around this foundation pit, which reduces the area of inflow for the water. So there is one diagram in literature how the inflow to the wells is reduced only if the wells are inside of the foundation pit. Otherwise, this won't help. So we have to go quite near to the aquitar to have a sufficient effect. So, for example, the enclosure should go to 60 meters, not to the aquitar of 18 meters, because in this case we would have no inflow at all. So down to 60 meters. First, if we calculate this situation, we have the same as before, because if the wells are outside of the foundation pit, this enclosure will not help us for the dewatering. We have to position the wells inside of the foundation pit. So I just can drag them with a mouse and shift them inside of the foundation pit. And if I calculate again and go to the page quantities, we don't have 68 liters per second required, but only about 26. So you see that in this case, 2 wells would be sufficient because we have much less capacity which is required. And this is printed in the results as well. You see we have a reduction factor from waterproof enclosure, and we have a reduction to only 38% of the original capacity. So in this case, we don't have 68, but only 25 liters per second which are required. This is one option where the sheet pile profiles reduce the inflow section for the water. A second option, if I double click again, is the so-called tight base, which means that we calculate a kind of trough construction method, which is a really closed foundation pit with a sheet piling and a base injected into the ground. In this case, we can calculate some residual inflow, which is very low because calculated per square meter wall area. So for example, 0.02 per square meter. And the base starts, for example, at a depth of 10 meters, has the thickness of 1 meter, and the permeability of 1 E minus 8, for example. As an option, we can define the inflow through the base per 1,000 square meters. Now in this case, we just want to pump the foundation pit empty. That means we have a certain residual inflow and our pumping capacity must be higher to have a certain capacity for pumping this volume empty, all the water which is inside of the foundation pit. And if we calculate this, we have a capacity of 18 liters per second with our wells. We have an inflow of about 10 liters per second. And the available pumping capacity is 54. And we have an inflow of about 10 liters per second. So 44 are available for pumping the foundation pit empty. And with 240 cubic meters of water in the foundation pit, we need a time of 1.5 hours to pump this volume empty. These are the two special analysis methods. And there's one thing we have to know with these methods. We don't have any formula to calculate the depth of the water level at any arbitrary point. This means with these two methods, we don't have the color areas to display. And as well, if we go down to the section, we can't draw the lowered water level here because we can calculate that. We can only show the original water level and the sheet piling and the base here over the length of the foundation pit. So this was the analysis method with vertical wells. There's another option if we don't have any wells entered here. And we don't have the special analysis method, so I switch this off. Then we have as well the option to calculate horizontal drains. This is after the wells, here the rubble drain or horizontal wells. And here we have three methods to calculate. One is that we just have one line of horizontal well. So it is one line at one side of the foundation pit. This is mostly used if there are very long and thin foundation pits. So we can work with one line. As an option, we can use two parallel lines, which have a certain distance. This would be 12 meters here, for example. And the depth must be lower than the foundation pit base. So this is option 2 with two lines. And the third option, which is the method by Davydenko, can be around an arbitrary shape. So for this option, I can change the shape of the foundation pit. Here we have the function terrain split. And I can enter here intermediate points. I stop the splitting with the right mouse button. And then I can just drag the points or double click for entering the coordinates. And this way I can change the shape of the foundation pit. And if I now edit this horizontal well to the type of surrounding the foundation pit with a distance of 1 meter, for example, again, negative is inside. And then we have this surrounding horizontal well. This is calculated by the method by Davydenko. And here we have the required pumping capacity. And if we go to the graphics, we should define a larger area to see the lowering. So in details for the graphics, we can enter, for example, 50 meters around the foundation pit. And then we see that here inside, for the horizontal wells, we always have the depth of the foundation pit, so the water lowered to the base. And we have higher levels here, 4 meters depth, 3 meters depth, and so on, in a greater distance. So this is the option for the horizontal wells. And one additional point, just to show it very short, if I delete the horizontal well, if we have many wells for vacuum wells, for example, we can as well use the option row of wells, and here define one row, for example, with 2 meters distance between the wells. So in this case, we will have 11 wells with a certain diameter along this row. We can change single wells, we can move them to other positions, double click and enter the coordinates. But always if we change the row again, for example, if I use a distance of 1 meter and 50, all these wells are created again along this line. So this is an option if you have very many wells along a large foundation pit, for example. And then one more option, which is quite nice for the display of your calculation. If I make a new example here, you have the option to import an image file. And this may be some plan, for example. And this image file first has no specific scale, which is independent from the real size. So we have to tell the program what is the real size of this plan. And for this, you see the diagonal line here. We can drag this starting point to any position, and to move it exactly to a certain position, we can switch off the grid. So this should be our first reference point. And the second point is drawn to this position. And now if we have the definition line at this point, we can double click at the edge of the picture and tell the program that the first point should be at the position of 0. And we have a length of 50 meters, for example. Then full screen. Then we see that these are now real coordinates which are running here at the top. If I go to the bottom left corner here, I have the coordinates of 0. And here at the end, we have about 50 meters. So this is a reference now to real sizes. And now I can create the foundation pit along or on this plan, along these predefined lines. And we want to calculate this shape of the foundation pit with a depth of 5 meters. And I need water level and aquitar. I need a soil layer again, down to the aquitar. And if I use the optimization for the wells, to bottom edge of 18 meters. So we need, let's look here, we need 5 wells for this size. And now if we go to the graphics, with a spacing of 10 centimeters depth, then we see that we have the colors a little lighter to see the plan or the map which is behind. So this is one option with the color areas. And I can as well use lines and use a larger area for display. So here we have colored lines with the labels of the certain depths from 4.70 meters to 8 meters, for example, at the well. So this way we can have our result printed on a map or on a plan to see the situation much better. So far for the different analysis options, we had the free inflow in the foundation pit, we had the waterproof enclosure, we had the trough construction method, we had horizontal wells, and we have the option to import a plan as a background for the graphics.